Okay, so the first thing is to grab the base surface out of your Workshop 1 base file that you've downloaded from the box. Just hit Control-C to copy that YAS base surface, and then go to File, New Document, and let's drop it in to get started. I'm just going to enable the preview for that to have a look at what we're dealing with, and turn on my high quality preview up in the top right corner there, the little blue sphere. And what I've modeled here, just to get started as a way to kind of sketch this out a little bit with you, is just a portion of that surface that floats over, right? So just this kind of leftmost portion over here. And the geometry is close, it's not exact. Again, this is a sketch, an approximation of how to model something like that. Okay, so if you looked at it, if you watched any of the other tutorials for this workshop, you'll see that what we've been doing is subdividing these surfaces into patterns or into paneling routines. We're going to do that here again, so we're going to go to Lunchbox. This is one of the add-ons you've installed. And diamond panels is the first option there in the panels box. Okay, and I'm just going to kind of get a start here by turning off my original preview, and we know that we need to add our custom values into these U and V inputs here to change the resolution of this so it appears a bit more like our building. So I'm going to go to Parameters and grab a couple of panels, and I'm going to type in 160 for the U input, and which gives us a pretty good approximation already. But I'll copy and paste this as well, and I'll just kind of drop that down to 16 and put that into my V. Okay, and just kind of overlaying this over the photograph, I've come to realize this is based on the scale of the surface I've modeled, is good enough to get the point across. Now, as we know from the building, there's a bit of a space, or it's a bit of an offset, I suppose, between the panel itself and the structure that it's connected to, right? Because there's this post that comes off, there's this little ball joint here, or spherical kind of node here, and into the node there are these connectors. Okay, so the panel itself is offset away from the structure a bit, and it allows for that rotation to be easily constructed. So what I need to do is offset this base surface to draw my structural grid. We've already drawn the kind of the base, at least for the panels, but we want to situate them relative to a structure that's just below. This is a topic we discussed a little bit last semester. But to do it here, I'm just going to go into my Surface tab, go over to Utilities, and find the offset component right there at the bottom. And this is going to produce a new surface offset from its original, based on the D input that you have here, which is the distance. And I'm just going to use a slider for this. So Parameters, Slider, should be familiar with these by now. And as you can see, if we change that value, the surface appears. So it's being drawn, right, in this case, to the inside of the original. And that's fine, because we can use this one for our structure, okay, to define our structure. And I'm going to leave it at around, I don't know, 0.5 or so, just for now. And we could turn that off. We don't actually need to see that surface, because we're going to repanelize it using this system again, right? But in this case, we're just going to extract the lines instead of the panels, right? Okay, so copy and paste that same diamond component and plug in the new surface. You can reuse those same U and V inputs. We want that to be the same. And you can see that we've basically redrawn the same paneling routine on this interior surface now as we did on the outer one. And that's good, because now there's a direct relationship. Each one of these panels correspond to one another, which means the structure will correspond to the skin. We could turn off the preview for that and go to Surface, and in the top left here you'll see BREP Edges in your analysis box. Let's just turn that on, because this just draws the line work representation of that inner paneling routine. Okay, and this is what I mean by kind of just setting up the framework for the structure. We're not going to go much further than this in terms of the structure itself in this tutorial. We're just going to focus on the panels, but we'll kind of connect back to this later on, just to kind of get a sketch of what the structure might become. All right. So the next step now is to work on our panels, and we want to offset them a bit to hold them away from one another dimensionally, and also we're going to flatten them, right? So we're going to remove any curvature that still might be there Um, and we're going to make them flat again to approximate the glass panels that are in the building. So the first thing we're going to do is go to surface again, and in our analysis box we're going to find the area component, and we're going to measure the area of all the diamond panels. Okay, don't worry about the triangles for now, we'll talk about that later. We're really just dealing with the diamonds for now because these are the ones that are actually rotated. I guess if I pop this up you'll see what I mean. The triangle panels here stay let's say perpendicular or orthogonal to the surface. These are the ones that are rotated, right? So we could just focus on those for now. We're going to end up using this center point to analyze a couple things in the surface. One being, first of all, where the true center point is, and also where the perpendicular direction of what the perpendicular direction of each one of those panels actually is, and we're going to need that for our rotation, right? We're going to need that as an axis. Okay, so in your surface tab, once again, in analysis, there's a couple things to grab, one being the surface closest point component, and the other being the evaluate surface component at the bottom left. We're going to plug in our center points into the P input of surface closest point, and our surfaces are the ones that are coming out of the diamond paneling routine. And this doesn't look like it did much. All it really did is ensure that the points that we've drawn before are actually interacting with the original surfaces, and it's also giving us this UV output, which we'll need to find our frames. And this will become clear in the next set of steps. But for now, go ahead and plug your surface input into the S of evaluate surface, and use the UVPs as the UV input of that component. Now, you're going to probably see something similar to this, where suddenly everything went pretty dense. And what you're looking at here is just a representation of the frames or the planes that are perpendicular to, actually I should say that are parallel or in line with the surface at that particular point, right? So every single point on a surface can be evaluated by the point itself, its normal, which is its perpendicular direction, and its frame, which is going to be the plane basically that's in the same, it's going to be at the same orientation as the surface itself relative to the point that you've chosen. You can change the size of that by going up to display and preview plane size. By default, mine are at 1. I guess I could change that to 0.25 or something and make it a little bit smaller. And you can see now that our preview is a little bit easier to deal with. What I generally do, though, is just turn this preview off because we really don't need to see that. It gets a little bit heavy on screen sometimes. We have the data and we can use it in the next step. Now, before we start rotating stuff, we're going to use that center point coming out of here as a way to accurately scale the panels into a slightly smaller version so that there's a little bit of an offset between them. Okay, so I'm going to go to the Transform tab up at the top, and over in Affine, the first component there is Scale. Okay. And what are we scaling? The geometry are the diamond panels, of course. And their center points need to be relative to each of the panels individually, otherwise we scale them all as a group, right? So here we're scaling the entire surface condition, the kind of paneled surface. Actually, what I want to do is scale each one of these independently by keeping them in place. So what I need is their center points, which is easily found here. Okay. And a factor. And the factor of scaling is something between 0 and 1. So I just grabbed another slider from the Parameters tab there, as you know. And I can change that value to go back up to 100%, about half scale here, and down to nothing, which of course will throw an error. Okay. So we have our little scaling capability, and we're just going to drop that down to like 0.9 or something. I think that's just about enough of an offset. And again, we're just doing this visually to get a start on this. And I'm going to turn off my points because I just like to keep my previews as clean as I can. To be honest, we can also probably go back and turn these edges off if you want, so that we can really just focus in on what we're working on, one thing at a time. That's a good habit, I suppose. Okay. All right, so we have our scaled geometry, which is the thing that we're going to actually rotate, right? But before we rotate it, we still need to flatten it, right? So we still need to find a flat plane to orient this on, because although it may not appear so, if we were to do a check on these to see if they were indeed flat, we would find that many of them aren't. Maybe I can try to zoom in and show you that. But some of these are going to, so for example, this point and that point relative to these two are not on the same plane. You can kind of see it a little bit here. It's hard to tell. It's very subtle because there's pretty high res on this. But they're not quite on the same plane, so it's a little bit twisted there. So you're going to get a little curvature in that. So it's not a good representation of the flat glass panel. Okay, so let's do the next thing here, which is to take this apart, find the 4 points, and then project them to a flat plane that we've already found using this component. Okay, so go to Surface, deconstruct BREP, which looks like this exploding cylinder. And what we can do then is do just that. We can kind of take that apart, turn off our original preview here so that we don't get too confused. And if we zoom in a bit, we can see that we've now revealed the 4 corner points at each one of those diamonds. Okay. I like to turn this one off and just kind of output the data that I'm working with at any given time. It's just a little bit of a workflow habit for me. And here's the points that I'm dealing with. And like I said before, what I want to do is make sure that all of these points that exist at the corners of those diamonds are actually on the same plane. And I'm going to project, I'm going to use the project tool to do that. Okay, so go over to the transform tab again. And you'll notice in the affine box there is a project component. Not project along, but project. Either will work, but this one's a little easier. The geometry they're projecting is all of the points, right, as we just said. And if we hover over P, it's looking for a projection plane. Now, right now, it's by default world XY, which is why all the points got basically just projected straight down. So we have a nice kind of 2D representation of it, which is kind of nice, actually. But not what we want. So what we need to do is make sure that they're being projected to the right plane, and the plane is going to come, that information is going to come from here, because these are the frames that are being derived from each one of the surfaces independently. But in order to get this to work properly, I need to make sure that my data is matching, right? And I go over this a little bit in one of the other, I guess it's the Smithsonian video. But I'll review it again here. So remember that this is an output of a certain number of paths or lists on the side, right? And those are in the curly brackets. Next to it says n equals 4. That is basically a collection of points, the 4 points that exist along each one of the surfaces. All the data to the left of that is basically describing each one of the surfaces. Okay, so it's basically one surface, 4 points in order. And there's quite a bit of surfaces we have here, right? So we have a lot of data. We have 1,193 surfaces. Here we've got the same number of frames, 1193, except it's not organized the same way, right? This is just one single list. I need to change that so that this kind of chain link line matches, or the other way around. This line needs to match this here. So what I can do is simply right-click on that F output and choose the graphed option, right? And I've changed the nature then of that data structure to match what I'm comparing it to. So now what this means is when I input this into here, I won't get any issues, I won't have any errors, and I won't crash my computer because the right number of data is being compared to the right number of data. So 4 points are being compared to one frame in the same way that 4 points come from one surface. Okay. Now this doesn't look like it did a whole lot. But if we zoom in close, we can see that there is a slight deviation, right? So the new points are different than the old ones. And you're not going to see a whole lot of action here, and that's because those panels were very close to flat, but they weren't perfectly flat. So now these are the points that we can use to rebuild the surfaces to make sure that they're flat. And to do that, we can just start dissecting each one of these groups of 4. By revealing each one of the points and then rebuilding the surface using the right component that can do that. So first go to Sets, and in the list box we can find the list item component. Okay, And zoom in on the list item component. It reveals a little plus sign, and hit that a few times until you see 3 outputs, right? 1, 2, and 3. What that's doing is showing us all 4 of the points in each one of those lists. And we can turn that one off because now we have a redundant set. The next thing now is to use these 4 points to rebuild new surfaces. And I'm going to go to my Surface tab, Freeform, and 4-point surface. Okay? And then I'm just going to connect across. Same way like we did in some of the other examples. And there we go. All right, so this looks very similar to what we had before, but it isn't. If you were to run a routine on this to check whether or not each one of these is planar, you would find that they are, because all of the points now exist on the same plane. So by definition, they're planar, which is good. So now we have our glass panels ready to be rotated. And that is the next step. All we need to do is figure out which rotation component is the right one. And because all of these panels are in 3D space, what we need to do is rotate 3D. So I'm going to go to my Transform tab here. And under Euclidean, I'll find the Rotate 3D component. It's the second one up from the bottom. The geometry that I'm rotating is our new surfaces. Here we have an angle input, and right-click on that to change it from radians to degrees. Okay, so right-clicking on that will open up this menu. You'll see that there's a degrees option there. Go ahead and do that, and you're going to start seeing some geometry being drawn here. But of course, it's not drawn properly just yet. And I'm going to go and I'm going to turn off my old ones so that I don't get too confused. So now I'm just looking at the rotated version. Let's see what else we need. We need a center of rotation, and we also need an axis vector or an actual line that we can use as an axis. This is important because each one of these panels here has its own axis of rotation. The axis of rotation is basically the long diagonal through the diamond. So it's going to be from the top to the lowermost point in each one of these. That's a different angle for every single one of these panels. So this cannot be a generic number, or it cannot be a generic, let's say, z direction. All the rotation angles have to be specific to the orientation of each panel. So what we're going to do is go to Curve tab and just grab our line component here. And because I've done this a couple times, I know that the first one and the second one and the fourth one indexed as 1 and 3 are the right ones to choose. And it's drawing a line from the upmost. Basically, it's drawing a vertical line from the top to the bottom point. We can use that as our axis. Okay, so let's drop that in there. And things are still going to look goofy just for a second because we haven't set our center points yet. And now to find the center point, we may be able to go back and reuse this point. But because we have a new surface, right, we've redrawn things over here, we probably want to update that center point, right, because now I think it's a little bit different. So you could either find the center point like we did before, but for the sake of maybe showing you another way to do it, or even just for time, I'm just going to go to my curve, and I'm going to find the point on curve component right over here. And by default, it's at 0.5, which is a location based on its parameterization. Lines, if drawn in Grasshopper, are parameterized between 0 and 1, so 0.5 is the center point. And I'm going to then plug that in into my Rotate 3D component. Okay. And then I don't need to see this, so I'm going to turn that line off. Now all we need to do is update this rotation angle to something of a degree. So I'm going to grab a slider for this, and this time I'm just going to double click in the area here, the gray zone, and just type in 90, and then click the little slider option here. And what that did is it drew out a slider for us between 0 and 100. And I'm just going to put it at around 35 and plug that into my angle input. And now what you'll see is that every single one of those diamonds have been rotated independently using the axis that we set up for it, right? Producing the effect, a very similar effect that the building has. And if I scroll around and kind of rotate around, we'll see that we're actually getting pretty close to what we need here. This is a pretty close representation, I would say, of the building, because if you look at a couple of interior photos, like the one that does this, you'll see that, surprisingly actually, that the panels actually are all rotated to the same degree, which means that on one side you get visual porosity from the inside looking out, and on the other side you get visual, a blockage, right? You don't have the visual porosity. That, of course, changes if you look at it this way. So we get some visual porosity in there. Well, I guess it doesn't change. It's about the same property there, yeah. But you get the idea, is that on one side it seems porous, depending on what angle you're at. On the other, it's the opposite, and that's true no matter how we're looking at this thing. In an extended version of this video, I'll show you a version that I put together that changes that a little bit and rotates them relative to their position along this kind of symmetrical form. And we'll look at that in just a second. So what I want to do now is, though, is kind of wrap this up, and I want to turn on my structure once again so I can get some, visual relationship again between the panel and structure. And I think it's maybe a little bit too far away, so I'm going to go all the way back to the beginning and change the distance of that offset, maybe to something a little bit closer, like that, maybe 0.1 as a proportion. Yeah, now my offset, I think, is a little more reasonable. And again, this is just a framework, right? Just a sketch. Okay. Last thing then, before we kind of look at the one of my fancier versions, I guess, is to just try to make a connection between the panel and the structure. Okay. And to do that, we're just going to have to connect some of the dots. So we're going to find some points, again, by deconstructing these surfaces, and start connecting the proper dots to the structure so that we can kind of get some representation of that as well. Okay, so the first thing we're going to draw is a connection. Let's look at the image again. So we're going to kind of draw this long post connection that goes from the original structure to the offset one, the one that kind of hangs out between the corners of all those diamonds. All right, so we're going to draw that one as a kind of an extension. We're not going to draw the sphere because it's a little bit heavy on the computer. We don't really need it. We'll represent it as a point, the node there. But let's draw that first little extension. And okay, so in order to do that, I need to find, again, the corner points, because really all that is connecting the corners of of the structure to the surfaces. And we know that there was an offset between them. So go to Surface, deconstruct BREP, and we can grab first those and turn off the previews. We don't need to see that. Copy and paste that deconstruct BREP so that we can do it again for the offset. And there we go. And now it's just a matter of connecting those dots together and extending them. All right, so go to Curve and grab your line component and go ahead and draw in between the V and the V, right? So the vertices of one and the vertices of the other. And the reason why this works, again, is because the diamonds are all ordered in the exact same fashion between the two control surfaces, because they're drawn using the same method. Now, what I like to do here too is kind of extend this off a little bit, because remember, these go a bit beyond. It gives this node a bit of tolerance, a bit of flexibility in terms of where it's connected. And I think it'd be nice to see that. So I'm just going to go to my Curve tab again and click on the Utilities and find Extend Curve up at the top, and just kind of draw out an extension of this. Now this is going to be bored in orange until I put in a value for both the start and the end, even if one of them is 0. So one of them is going to be 0. So the start point, I don't want to extend from that angle. I want to extend only from the end point. So I'm going to input a panel that has a 0 value in it to the L0. And then I'm going to use a slider to figure out how far I want to kind of extend in the other direction. Now it looks like I've gotten that wrong, actually. I need to actually extend. It's just because of the way that I input this. So if I would have input this V into here and that went into there, then I'm going in the right direction. It's just that I got that twisted a little bit. So depending on the direction of the line, right, where you started it and where you ended it is where these inputs will start to make sense. I could have swapped this input and that one, or I could just swap the inputs into line. Either way, it's fine. And you can see that I'm now drawing that longer toward the outside of the structure, which is kind of how it's built in reality. Okay. The next thing then is to connect the panels, okay, to that post, right, to that structure. And one thing that I think we can do, first of all, is to visualize where that joint might be, the node, and that node is going to be at the original intersections. So it's going to be one of these sets of vertices for the paneling. Okay, so we could figure out which one came from the paneling, which is this top one here, and just kind of put a little point parameter on that, right, to kind of reveal and show where that location was before we started doing the rotations. And that's what I'm going to use as the connector, I guess, or as the kind of location for that node. And that'll help me determine how far I want to make my extension too, right? So I can kind of do something like that, because it seems about right. Okay. The last thing then is to just kind of deconstruct the rotations, right? We've got all that rotated surfacing. So let's go back to surface, deconstruct, and input our B-rep into there. And we can turn that off because all we want is the points. And now we just got to do a little bit of connecting of the dots as well. So we'll go to curve, line, and start drawing some new lines in between. So the start point can be from the corners of our rotated panels. And the end point will end up being the corners of our originals, right? So that's actually these, right? And now that's basically drawn for us the kind of stick-like connections that we'll see in the image here, right? These the little connectors from the node to the panel itself. Okay, and to kind of clarify all of this, I guess what I'll do is I'll start putting a color on this stuff, right? And I'm going to go to display, the display tab, and under preview there's a custom preview option. And over in parameters you'll find under the input box you'll also find the color swatch. So let's start putting a little bit of a representation on this stuff so I can really get a sense for what I'm looking at here. And I'm going to plug in my extensions to turn those white so that I know that those are part of the structure. I'm also going to take my original, these lines that we drew a long time ago for the underlying structure. I'm going to hold down shift and plug those also into that preview so those turn white. Okay. And now the last thing is just to kind of color these other ones, these connections, as something else. And actually I'm going to color the node something else. So I'm going to grab two more displays, all right, because I'm going to add two more colors. And I'm going to grab two more color swatches. And I'm going to click on the color swatch in the kind of white area there, and I can go ahead and change my colors. So I'm going to make one of them black. All right, I'll make those connections black. And then this node, I guess I'll turn that kind of a bluish color or something. Something like that we can see. Right? And now we've got a visualization on screen that's a little bit more clear in terms of what's what. Right? You can kind of see it a little bit better now. We've got a node, a connector to the structure between the node and the steel structure beneath, and then the connections between the node and the panels themselves. Right? And it's a little bit easier to see now that we've colored everything. Okay. And that pretty much wraps up this section. This talks a little bit about some of the basics of surface description and then kind of using an axis to rotate each one of these panels to a particular degree. And if we zoom out a bit and change the rotation angle, of course, you'll see that everything will either close down or open even more. And it's kind of a nice kind of wave-like effect because our camera is stationary. And we get a kind of a nice effect of that there. Okay. And before we close off on this one, I did just want to show, I'm not going to go over it with you, I can give you the file, but I did just want to open up a file for you that kind of expands on this a little bit. grab that. Okay, and now what you're seeing is, let me just show you the script. It's just the expansion of it really is kind of breaking the data down into basically two sets down the middle. And I've identified a center line, and that center line is going to be rotated to a degree of 0. Basically, it's not going to be rotated at all. And everything that's furthest away from that, going off in this direction and in that direction, are going to open up to the maximum angle that I set, but in the opposite direction, right? So that means that when I look at this side of the structure, I'm getting, from the front, I'm getting some visual porosity. And as I look at this side, I'm also getting visual porosity, right? So it means that they kind of fan out from the center, so it's a more symmetrical structure, unlike the one that we've modeled in the example together. The other thing I did is I added a custom color relative to the rotation angles. So the higher of the degree of rotation, the darker blue it becomes, and all the way down to 0, the more pink it becomes, okay? And there's just a custom gradient that I applied to this. So in the middle is where all the zeros are, and these are my maximums. Okay, so this is a representation of the colors that I'm getting based on the data in terms of how I set it up. Okay, we've done, this is a kind of an enhanced version of some of the things we did last semester in terms of setting up ranges and being able to control our max and mins, and then everything in between is basically a gradient of those two numbers. So 45 over here, 0 over here, and everything in between is a smooth gradient based on its location. So if I change this number to, let's say, 90, which is kind of high, and then negative 90 to affect the other side, you'll see now that they're really rotated, right, quite a bit more. They're rotated 90 degrees off of their axis, but they still come all the way down to 0 regardless. This can also be updated. I can change this to, let's say, 15 if I want, and make that my minimum. But that's not exactly a great idea because it doesn't really fix, it doesn't really kind of follow the logic that I tried to set up for this one, which was a kind of a symmetrical condition where these fan out and kind of rotate out in the opposite direction as these, so that we get the same effect on the other side. But just to show the control a little bit, there's that. All right, so I can share this file with you. You can feel free to take it apart and see if you can rebuild it on your own. I just wanted to show kind of an expanded version of this one, and also our ability then to kind of identify a color gradient based on the kind of the rotation data that we've applied to each one of those panels. So it gives us an idea for it basically produces an aesthetic visualization of the numerical information that we used to rotate all the panels. Okay, that's it. We'll see you next time.